learn like a pro.
All right, let's get right into it. We see things moving all around us, every single day. But how often do we really stop and think about how it all works? Today, we're going to go on a little journey. From the perfect, straight lines you see in physics textbooks to the messy, beautiful curves of the real world, all to understand what's really going on when something falls.
So right off the bat, you can see two totally different stories here. Over on the left, you've got this clean, predictable, straight line. That's what we call uniform acceleration. But on the right, it's a jagged, unpredictable curve. That's non-uniform acceleration. Think of it like this. The straight line is a car on a wide-open highway, and the curve, well, that's the same car stuck in rush hour traffic. And as you're about to see, most of the real world looks a whole lot more like rush hour.
So here's our game plan. First, we'll look at what happens when acceleration isn't constant, when it changes from moment to moment. Then, we'll figure out how to actually read these complex motions using graphs. After that, we'll build a model for a perfect, ideal fall, and then we'll bring it crashing back to reality by adding air into the picture. And finally, we'll put it all side by side so you can see the whole story. Okay, let's dig into that fundamental difference. What is it that really separates that smooth highway ride from the stop-and-go traffic? Well, it all comes down to how velocity is changing over time. You see, it all boils down to consistency. With uniform acceleration, that car on the open road might add, say, 20 meters per second to its speed every single second, just like clockwork. But with non-uniform acceleration, a rush hour car, that change is all over the place. It's way more complex, and honestly, a much more realistic picture of how things move. And that's really the big takeaway here. This messy-looking graph, it's actually normal. From a gust of wind hitting a bike to a driver tapping the brakes in traffic, real-world motion is almost always non-uniform. And that's exactly why we need the right tools to make sense of it. Which brings us to our most powerful tool, the graph. These aren't just squiggly lines, they're like a language that lets us read the story of an object's motion, even when that story is constantly changing. Now, the secret to unlocking these graphs is a concept called the gradient. It's really just a fancy word for the slope of the line. And on a velocity time graph, that gradient, or that slope, tells us something absolutely crucial: the acceleration at that exact moment in time. So here's the clever part. How do you find the slope of a curve? Well, you can't, not all at once anyway. But what you can do is draw a straight line that just barely kisses the curve at a single point. We call that a tangent. And the steepness of that tangent line tells you the object's exact instantaneous acceleration. A really steep tangent means it's accelerating hard. A shallow one means it's barely speeding up at all. Pretty neat, right? Okay, let's take these ideas and apply them to one of the most basic types of motion there is, free fall. But to really get it, we've got to simplify things first. We have to imagine a perfect world. Now, why would we do that? Simple. By getting rid of the complicating factor of air, we can isolate the one, single, constant force that's running the show, gravity. This gives us our perfect, idealized starting point. In this perfect, airless world, this vacuum, gravity pulls everything down with a constant, unwavering acceleration of about 10 meters per second squared. This one number is the bedrock of our ideal fall. So what does that number actually mean? It means that for every single second an object is falling in a vacuum, it gets 10 meters per second faster. It's like the universe has its foot slammed on the gas pedal, adding about 22 miles per hour to its speed. Every single second. It's relentless. And just like that, we're right back to our nice, clean, straight line. You see, free fall in a vacuum is the perfect real-world example of uniform acceleration. The gradient of this velocity graph is constant, and its value is always about 10. Simple, predictable, but as we know, it's not the whole story. So it's time to step out of our perfect vacuum and back into the real world. A world filled with air. And this introduces a brand new force, one that complicates everything. We're talking about air resistance. This is the million-dollar question. The second we introduce air, the rules of the game totally change, because now there's a force actively fighting back against gravity. Let's break down how this tug-of-war works.
Right when you drop something, its weight is the main force, pulling it straight down. But as it speeds up, this upward force, air resistance, starts pushing back. Now here's the key. That upward push isn't constant. It gets stronger and stronger the faster the object falls. The downward pull of weight stays the same, but that upward push from the air just keeps growing and growing until the two forces perfectly balance each other out.
And that exact moment of balance, that's what we call terminal velocity. The forces are equal, so the overall net force on the object is zero. And if the net force is zero, acceleration stops. The object doesn't stop moving, of course not, it just stops getting any faster. This is the very principle that makes parachutes save lives, and it's why even the fastest raindrops don't feel like tiny bullets when they hit you.
Okay, so now we've got our two scenarios. The perfect, ideal fall in a vacuum, and the real-world fall through the air. Let's put them side by side and really see the complete picture.
And boom, this single image tells the entire story. On the left, in a vacuum, the velocity just keeps increasing forever in a perfect straight line. But on the right, here in the real world with air, the journey is totally different. The line starts out steep, almost exactly like the vacuum graph, but as the object speeds up and air resistance builds, the gradient, the acceleration, gets shallower and shallower. And finally, the line goes perfectly flat. It hits a plateau. That plateau is terminal velocity. The gradient is zero, which means the acceleration is zero.
So let's just break it down one last time. In a vacuum, it's simple. Only gravity is acting, so acceleration is constant and the graph is a perfectly straight line. But in the air, you have two forces finding it out. This makes the acceleration decrease over time until the object finally hits its terminal velocity, creating that signature curve that flattens out at the top.
That really sums it all up, doesn't it? Our ideal models, our laws of physics, they give us this amazing framework for understanding the universe. But it's in the real-world complexities, like air resistance, where the truly fascinating stuff happens.
So, if you're going to remember anything, remember this. 1. Most motion in the real world has changing, non-uniform acceleration. 2. We can measure that acceleration at any instant using the slope of a velocity time graph. 3. In a perfect vacuum, everything falls at the same constant rate. And 4. Here on Earth, in the air, falling objects eventually hit a top speed called terminal velocity.
And in the end, that's the journey we just took. We saw how those clean, simple straight lines from the textbooks can elegantly bend and curve to describe the rich, complex reality that's all around us.
And that leaves us with one final thought experiment to chew on. Imagine a bowling ball and a single feather. You drop them at the exact same time, but you do it inside a perfect vacuum with absolutely zero air. Which one hits the ground first? The answer, well, it lies in the very first principles we covered today.